In the previous lecture, we looked at an operator that was related to the time evolution operator of a quantum state, and we found that it needs to be a unitary matrix, which we wrote as the definition of a unitary matrix was that U dagger U was equal to the identity matrix, where again, remember, U dagger essentially means the Hermitian conjugate, we call it, is the transpose complex conjugated. So we flip all the elements around the diagonal, and we take the complex conjugate. So if we take an arbitrary or just some matrix element, it's called IJ. The Hermitian conjugate of that is going to be UJI. That's flipping row and columns, complex conjugated. Now, what we want to do here is look at another type of operator that's related to things we observe. And so we'll put the constraint out first. So what about observables? So these are properties of objects that we measure in experiments. And recall that, well, it should be clear that whenever we do an experiment, we get data out. Whatever we measure, all those properties are real values. So we're always talking about outcomes of experiments that yield real numbers. We don't measure something and obtain complex numbers. So what we want to do is consider operators that have eigenvalues that are real. We want to restrict to those operators that have real eigenvalues. And those are going to correspond to operators or observables that can be observed in nature. So let's look at a particular form of operator, and we'll see why it's called this. But let's consider an operator. I'll call it L, where L is equal to its Hermitian conjugate. So that means when we flip around the diagonal, we take the complex conjugate, we get the same matrix back. This is what we call a Hermitian matrix, or a Hermitian operator. That defines Hermitian. So this is a different type of matrix, if you will, or operator. What we want to do here is to show that if we have this constraint, it's the eigenvalues of a Hermitian operator are real. So to do this, let's assume, well, we don't assume, but there is a basis of eigenvectors and eigenkets for this operator, L, and we're just going to do this abstractly. This is a standard derivation I'm going to do that's often done in higher courses, so this is not going to be really expected of you, but we do want to introduce it here because it's a very simple proof, but it's a very nice proof, but it is something that later on you'll be expected to reproduce in a higher quantum mechanics course. So let's take an eigenvector. We'll call it lambda. We use the notation of Susskind, and it's going to have the eigenvalue lambda. And right now we're not making any assumptions on whether lambda is real or complex. So recall that's what the definition of eigenvector is, we defined before. And also what we learned in the previous lectures, if we want to convert this to a bra, how do we do that? Well, again, what we do is for the matrix, or the operator, we turn the ket into a bra, and then remember the operator becomes Hermitian conjugate. And when we do it to this side, remember when we take our kets to bras, we get lambda here, but lambda star, because we're doing the transpose as well, and the complex conjugate as well, I should say. Okay, well now notice if I can look at this in various ways, but let me act on both of these with the corresponding bra. So that means I'm going to go over here, and here we're going to squeeze in a bra there. Let me rewrite that. We'll pull out the lambda. It's a scalar. Oops, that's a lambda on lambda. And we do the same here, where now we multiply by the ket of lambda. So this is going to be lambda star, lambda on lambda. So now, notice what we have. Let's subtract these two. So I can write this in different ways. Let's write it this way. So I'll take L minus lambda L dagger, or Hermitian conjugate of L. That's another way to say that. And then on the other side, I just have lambda. I'll factor it out. I'll do this quickly. Minus lambda star, parentheses, lambda on lambda. Now we're going to make the assumption that Lambda is normalizable. It's not 0. And what that says is that, well, if we have a Hermitian matrix, then this is equal to L, and this side is equal to 0, which that implies that lambda is equal to lambda star. And the eigenvalues are real. So this is why we state that physical properties are represented by real values and real eigenvalues, and they're represented, the observables represented by Hermitian operators, or matrices, if you will. So it's just a quick little proof of that.